All right, so the third state, we said there are three states at any given moment. Your rigid body can be in one of these states. It's either in equilibrium, either in or in impending motion, or it can be in motion. Right? Not exactly the focus of this course, but you'll see that in dynamics. So third state is the state of motion. What's that? Well, I think the name kind of says it. If the magnitude of P becomes slightly greater than Fs, right? Fs was impending motion, the moment before the motion starts. So once your P gets to that level, a little bit more than that, your rigid body starts moving. Right? So in that case, when that happens, actually friction force drops. So the friction is important. The friction force, the magnitude of the friction at impending motion state, in that state, is larger than the magnitude of friction when the motion is happening. Right? So it increases and then it goes down a little bit and it stays there. So the magnitude drops to a smaller value. So let's put it this way. If the magnitude of P, right, you're talking about just that box again, we're just going with that example, becomes slightly, let's put it this way, becomes slightly greater than Fs, right, static friction, the friction force drops to a smaller value, and we call that Fk, kinetic friction. Right? So if I have my, again, box there, right, you have your, the weight is still there, right? Has some weight, W. Let me put it here. This is W. And then you have a force P this direction. Right now we are in motion, the state of motion. You have your friction. There you go. I just have to fix that. This is friction. And then you have your normal force, right? Somewhere here. So let's put the arrows. Friction is always against the direction of the motion, normal force. So your reactive force, you can think about it here. This is your reactive force. Now in this case, Fk, right, friction or kinetic friction is equal to mu k n, right? Now that would be the expression for your kinetic friction or friction when you're in motion, state of motion. You can refer to it as, you can write it this way. Kinetic friction force. We could write the other one as static friction force. Right? So in kinetic friction force, as we said, Fk is slightly smaller than Fs. Now, pretty much the same story, but now you see we are using mu k, which basically mu k is the, you can, you refer to that as coefficient of kinetic friction, right? So let's just put the name here. Coefficient of kinetic friction. This is also something can be measured, right? Same story when you pull, let's say you put a box on a surface, let's say you put a wooden box on a wooden surface, you pull that with some force, you're measuring the force, the motion starts happening, so you're pulling it, it's moving. During the motion, you can see how much force you're applying to keep that moving. Measure that force, knowing the weight of the box, you can easily find the coefficient of kinetic friction. And also the same story, you have this angle. This reactive force creates with normal force, you can call it phi k, and value for phi k, also we can find it as tan inverse, right? Whatever is the opposite, which is f. Well, let me put fk here, be more intelligent with that. Fk there. This becomes fk over n, or tan inverse mu k n over n. That means phi k or phi k is tan inverse mu k. And you refer to it as, you can refer to it as angle of kinetic friction. Angle of kinetic friction. Now, so typically what happens is that what you can do, and it's a safe assumption to make, is that typically the value of mu k, coefficient of kinetic friction, is about 25% smaller than the value of mu s, or coefficient of static friction. Right? So that's, if you know mu s, it's usually a safe assumption to make. Let's say you're designing some system and you want to know what is the kinetic friction force. You know mu s, you can just use take mu k 25% less than mu s, and that'll work. Right? So here is where we are right now. We said so we talked about friction, right? We talked about this magnitude. So friction is a force. It has a magnitude and it has a direction. The magnitude is its line of action. That's where we started, right? The line of action is tangent to the surface of points of contacts, right? That surface where the points of contact are. And that's the line of action, and direction is always opposite to the motion. So whichever the motion or possible motion is going to be, or whichever direction the motion is, friction is in the opposite direction when you draw the free body diagram for a system and you want to take into account the friction. The magnitude really depends on the state of your rigid body. Three possible states. It can be in equilibrium, meaning that the object is not moving, so whatever force you're applying is not enough to overcome friction to make that motion happen. So in that case, you typically treat friction as an unknown force, and you have to calculate that in your free body diagram, put it there as an unknown. As I said, where the normal force is applied, you can actually find it if you find the moment about the right point, like correct point, and somehow get rid of your friction force, unknown friction force, and not have it in your expression. The other two states, though, impending motion and motion, in those two states, you actually have your friction, you have expression, you have some expression representing your friction. So if you're in impending motion, we said the moment exactly before the motion starts, right? Fs is, we represent the value of friction force with Fs, calling that a static friction force. Fs is mu s n, mu s being coefficient of a static friction, n being the normal force. Right? Since mu s can be calculated, can be found, experimentally, or it is measured experimentally for different surfaces, because it depends on the surface, the types of surfaces that are in contact, whether they are oiled or lubricated or not. So mu s actually, typically the values for that are tabulated in design handbooks or different mechanical engineering references. And sometimes in all problems, sometimes you are given enough information to find μs from your rigid free body diagram. So that's one state. The second state. Third state would be when the rigid body is moving. Right? In that case, also we have an expression for friction, which we call it Fk, or kinetic friction force. Right? The magnitude of kinetic friction force is slightly smaller than magnitude of static friction force, and the relationship still exists between Fk and N. In this case, these two are related to each other through mu k, which is coefficient of kinetic friction. And we said that's also something that can be measured experimentally, or you can just say typically coefficient of kinetic friction is 25% smaller than coefficient of static friction. So if I wanted to bring this graph here. There you go. This is a pretty good representation of what happens. So this is friction, right? The vertical axis, y-axis is representing friction, and this is force P. You are applying. When you increase P, your F friction increases. It keeps increasing, right? It's the same magnitude. So before you get into the state of motion, they both increase. They have the same magnitude, right? Because whatever force P you apply, the friction force applies the same amount of force in opposite direction, and that's why your object or your rigid body doesn't move, right? So they both increase up until the moment you get into impending motion. So this is no motion. This is where you have impending motion. This is exactly the moment before the motion starts, and you have the value for friction there as Fs, right? Static friction force. And after that moment, that fraction of second, after that moment, when if you keep increasing force P, right, your rigid body, your system, your structure, your in this case box starts moving, and then Fk drops, right? Friction drops, and we represent that with Fk as kinetic friction force, right there. So this is if you want to measure friction in your system from the moment you start applying force P and you increase that force until the motion starts. This is what you get. If you plot friction as versus force P, this is what you get. So it increases, friction gets to maximum at impending motion moment. After that, it drops, and you'll get Fk. Right? Now, few things, or maybe two things to remember. First is when you have a slipping, right? When we talked about a tire of a car on a, let's say, icy surface, right? There's some kind of slipping happening there. No? When you have a slipping, right, or when it's about to happen, when there is no slipping, it's you are in there's friction there, and obviously it helps your car to move. Right? That's the purpose of the whole tire, and having friction between the tire and the road surface. Now, when slipping is about to happen, right, you're going to get Fs, right? That's impending motion. When a slipping happens, right, I give you the example of a tire because it's easier to imagine. When a slipping happens, right, then you have Fk. And you see Fk is smaller than Fs. So that's when you have a slipping and the tire is rotating, but you know, the situation that you want to be in when you're driving. So just keep that in mind. For circular object, it's a little more tricky. Let's say a cylinder, right, rolling on a surface. When the rolling is happening, right, you have a static friction, although it's moving. But remember, we care about the surface, contact, the contact between surfaces. So there is no slipping there. So when there is no slipping, it's a static friction. When this cylinder starts slipping, right, you have kinetic friction. Right? That's how I want you to think about a tire of a car or a cylinder rolling on a surface, because those are the cases that you have actually a moving object. So don't be confused that it's motion. It's not motion, right? It's all about slipping or not slipping. If there is no slipping, right, you're good. There is no slipping. You don't really have, you need to be worried about kinetic friction. It's static friction. If slipping is happening, you have kinetic friction. All right. So let's stop here. I'll go over an example, multiple examples, and we'll hopefully it gives you a better understanding or a better view of what the whole story is. How can we calculate friction? How do we draw free body diagrams with friction? What unknowns we can have? How do we generally deal with rigid bodies when we are taking into account friction, right? Added to those 4 forces that we know from before, all right?